moving to our next speaker for today. Is Jorge Nochebuena. He's from Cisneros Group at UT Dallas. So welcome, Jorge.
Thank you so much. Can you see me screen?
Yes, we can see your screen now.
Okay, thank you. Okay, hello everyone. I'm going to talk about QMMM simulations with the Gaussian electrostatic model. But what is the Gaussian electrostatic model? The Gaussian electrostatic model is, or GEM, is a polarizable potential that uses density fitting techniques to reproduce molecular electronic densities. These fitted molecular densities are used to calculate intermolecular interactions. And in the GEM, molecular electronic densities, density fitting is performed by minimizing the Coulomb cell interaction energy error, and GEM can overcome some known limitations associated with a discrete description of the charge density, such as charge penetration error or inaccurate anisotropic effects. The total energy in QM-GEM calculations can be written as shown. The first term is the quantum energy of the subsystem, the region of the subsystem calculated with GEM, and the interaction between the QM and the GEM subsystem. This term is divided into 4 terms. The first term is the Coulomb term. The second one is the exchange repulsion term, and the polarization term, and the dispersion term. The polarization is calculated using amoeba by approximating the QM wave function, and the dispersion is calculated by employing 3 terms of the dispersion expansion. The Coulomb term and the exchange repulsion term involve 3 center integrals between the quantum region and the GEM density. And here, K is a proportionally constant. The Coulomb term and the exchange repulsion term can be included in the effective Hamiltonian potential, something like this. And the fitting can be performed by Koleski decomposition or Tikhonov regularization. And to ensure that the total density integrates to the correct number of electrons, a total molecular charge constraint via a Lagrange multiplier is applied. And the proportionally parameter K is calculated via least square fitting to reproduce SIPT conformance. The QM and GEM capability has been evaluated on in this paper on a reduced set of water dimers reported by Paisini and co-workers. This reduced set involve monomers with bonds and angles similar to the geometry of amoeba polarizable force field. This set was divided into 10 groups using K-means clustering methods, and here are the results. This figure showed calculate a maximum uncycling error and the root mean square error, and for each contribution. For example, here is the Coulomb interaction, the exchange repulsion term, and the dispersion plus polarization, and this is the sum of this contribution. We can see, for example, the root mean square error is less than 0.05 kilocalories per mole for the Coulomb interaction. Is less than 0.15 kilocalories per mole for the exchange, and the polarization plus dispersion is a little bit higher, and this causes that the total energy is it has a similar error, but these errors are in the same range of amoeba polarizable for field comparing to the SIPT values. And returning to the total energy formulation, the second term is divided into different contributions. For example, in a previous version of GEM that is called GEM star, GEM uses the attractive term of the Halgren potential defined like this. This Halgren potential is only for attractive interactions because the repulsive interactions are already taken into account in the exchange repulsion term. In GEM star, the same fitted molecular densities expressed as an expansion of primitive Cartesian Hermit Gaussian functions are used to calculate the Coulomb interaction and the exchange repulsion term. In the new version of GEM, different forms of molecular density are used to calculate the Coulomb term and the exchange repulsion term. And in both cases, the densities are fitted to reduce the error for each contribution with respect to the SAPT DFT counterparts. In addition, a new dispersion and charge transfer term inspired by CIFA is proposed. For the fitting of the dispersion and charge transfer term, the ab initio reference values are obtained from differences between the Kopec cluster binding energy and all GEM contribution. For this reason, the dispersion and charge transfer test includes higher order many-body effects. And in the other hand, the polarization test is computed using the amoeba formulation, but using GEM multipoles, which can be derived from the fitted molecular densities. To parameterize the exchange repulsion and dispersion charge transfer terms, the ab initio reference data are based on the 10 Smith dimers calculated with this level. These specific dimers are representative for repulsive and attractive interaction. For the Coulomb energy, GEM star and GEM employ the same fitted densities. So they show a very good agreement with the reference that is SAPT. On the other hand, the use of separate coefficients in GEM and GEM star produce different results. For example, GEM star is GEM is in very good agreement with the reference, and GEM star is not. To parameterize the exchange repulsion and dispersion charge transfer terms, the ab initio reference data are based on the 10 Smith dimers. The new version of GEM is close to the ab initio reference, and interestingly, the binding energy for GEM and GEM star show a similar deviation. This result suggests that GEM star showed a compensation of errors. The performance of new parameters was evaluated in a linear scan of the canonical dimer along the OH axis. GEM star and GEM can reproduce the Coulomb energy for all separation distances. And for the exchange repulsion term, gem star and gem agree very well with the reference, and like in the column there, the polarization for both is similar for both, and it's not very good in this region, but agrees asymptotically at a long range with SIPT-DFT. For the dispersion and chunk transfer term, gem star and gem agree very well with the respective reference. However, gem is much closer to SIPT-DFT than gem star. In addition, gem star or gem can reproduce very well the binding energy from a copy cluster reference. To perform the gem parameters around one reference water, in this case, one water is kept fixed and another water molecule is rotated around the XYZ axis. In this case, I will show you only the results for y-axis, but similar results were obtained for x and z-axis. The column term from gem and gem star is in a very good agreement with the reference. For the exchange repulsion term, gem agrees very remarkable well with the SIPT reference. And the polarization is also in very good agreement. Regarding to the binding energies, gem star benefits from compensation of errors between the exchange and repulsion term, and while gem provides a better reproduction of each individual term. The radial distribution function of OO, OH, and AH per atoms has been also calculated. In all of them, gems agree very well with the experiment. Moreover, contains phase properties such as density or enthalpy of vaporization or even cell diffusion coefficient have been calculated at different temperatures. At room temperature, the density calculated with gem is closer to the experiment than gem star. However, gem overestimates the enthalpy of vaporization by about 1 kilocalorie per mole, while gem star is closer to the experiment. And finally, the cell diffusion coefficient here, gem star showed very good agreement with the experiment for a full range of temperature. In summary, the separation of Coulomb and exchange repulsion term using distinct frozen molecular densities and the implementation of a modified dispersion term significantly improved the gem water model. This new parameterization showed that each contribution from gem reproduced accurately the SIPT-DFT results, as well the copy cluster binding energies, whereas gem star agrees with copy cluster thanks to the dispersion charge transfer contribution. In collaboration with Andy Simonet from NIH, we were working on the implementation of gem in Sci4. The following graph shows that there is an excellent agreement between the previously reported values in this reference. Using this implementation, we compute the Coulomb term and the exchange repulsion term of 10 Smith dimers. In the graph is showing 20 dimers because the two possible options were considered. That is, in the first 10 dimers, one monomer is considered in the quantum region, and the other is calculated with GEM. And in the other 10 dimers is the opposite. So this result shows very good agreement for the exchange repulsion term, either using a set of the fittest using a fitted on the fly coefficient or using pre-fitted coefficient. The yellow line corresponds to when we use a Coulomb coefficient to evaluate the exchange, and the green line corresponds to the exchange coefficient to evaluate the exchange there. Surprisingly, the Coulomb term, the Coulomb energy, show a slightly more negative results for the dimers with more attractive energies. We think one possibility is because QMGM uses quarks, their own set of coefficients. We have all of the ingredients to calculate QMM simulations. So the next step is use Lichen to implement these separate contributions. And Lichen is a platform that is used to perform MM or QMM or even QM calculation with polarizable force field such as Amoeba. The calculations are performed by interfacing different software packages, including Gaussian, Sci4, Endoluchem, Tinker, or Tinker HP. And different kinds of calculation can be done, for example, single point energies, frequencies, geometry optimization, reaction path optimization, or Monte Carlo simulation. In a recent paper, we use Lichen to evaluate the performance of potential candidates for main protease of SARS-CoV-2. And for example, this result shows that this candidate is not good because the second step is very high. It's around 80 kilocalories per mole. And finally, I want to thank all of you for your attention and my research group, and I will take any questions you may have.
Thank you, Jorge, for your presentation. So please, the floor is open for questions. We are super on time. We have time for a couple of questions.
I have a question. Can I ask one?
Oh, sure.
Okay, first of all, I really enjoyed your talk, so thank you. And one question that came up is about how you generate the density. I understand you do a fit to fit the electrostatic potential, but it was not clear to me what happens when, for example, the water molecule vibrates. How do you determine that fit in a different configuration, or are the water molecules always static? I'm assuming they're allowed to move, right?
Yes, we use frozen densities. So the geometry is only one.
I see. Okay. And do you have ideas on maybe extend this to vibrating or non-static configurations of water?
As far as I know, the use of frozen molecular densities has been proved from different configuration, and GEM can reproduce the energy even if they are not in the same orientation or in the same configuration.
So if I may, just really quick. So the thing is, if there's distortions, either like angular or in the bonds stretching, because we're using also the bonded amoeba, we've in the same QMGEM paper of 2018, we reported that the densities are, I'm gonna say, forgiving with a star, with an asterisk. So the deviations are not huge for, let's say, plus minus 0.15 to 0.20 angstroms stretch, and like 10 to 15 angstroms plus minus, which is what we observe when, for frustration in clusters. So it's not terrible.
Okay. Okay, thank you.
Okay, so we have more questions for Jorge. Okay, so if we don't have any other questions, so I think we can move to our next, the last
Maybe
presentation.
Maybe we should wait. No, don't we? Shouldn't we wait until 1:30?
Also,
Yeah. Yeah, we should. Which means there is more time for questions.
I have a question. Can I make a question? Okay. So you show for your dimer for water, for the water molecule, the binding energies. So my question is just how you determine these binding energies?
The binding energies?
Yes.
The binding energies are the sum of different contributions: Coulomb, exchange repulsion, polarization, and dispersion.
Okay. Thank you.
Okay, can I ask another question? Potentially not very smart question, but could you go to well, I guess my question is a general question. I guess, why are you doing this? You can use soft electrostatics, right? By just softening the potential rather than the charge density. So then naturally to ask, why are you instead choosing to make a broad charge density rather than a broad potential?
Because water is difficult to simulate. There are many polarized force fields, for example, to simulate water, but there are some kind of errors that a GEM can overcome. For example, the charge penetration error or the anisotropy effects, for example. And another is because no, sorry, I forgot. But basically, we are trying to develop a force field that is accurate, and you can consider, for example, quantum effects in this model. For the potential is very quick when you use a perfected coefficient.
Okay, thank you.